Hello, everyone. Welcome back. Good afternoon. I'm Steve.
And I'm Scott.
And together we are Backyard Musings, the Science and Technology channel.
And we are talking about space today. And
I really love this topic we got today. And you take a look at your screen, you're going to see all these accretion disks for planets that are forming. This is just tip of the iceberg right here. And if you want, go ahead and pause the video and read what's underneath here. Let me see if I can get it so where you can. There you go. That way you can scroll, zoom in, and read the text. Anyways, the reason I like this, Steve, use your words. I'm so excited. That this is the creation right here. We're seeing it billions of light years or whatever, millions of light years away, but this is how Heavenly Father created and how He still creates our universe and our world, and we're watching it live. It's pretty awesome. Pretty awesome.
Okay, let's talk about it.
New high contrast images from SPHERE, that's an acronym, show a stunning variety of debris disks shaped by collisions of tiny planet building bodies. The structures often resemble our asteroid and Kuiper belts, hinting at unseen giant planets sculpting the dust. By comparing 51 systems, astronomers found clear trends linking star mass to disk mass and size. These images lay the groundwork for future telescopes to uncover the planets responsible for these patterns. Would you like to know more?
Using the SPHERE instrument on ESO's Very Large Telescope, astronomers have assembled an unprecedented set of images of debris disks in distant planetary systems. These are wide, dusty structures made of tiny particles that orbit other stars and trace the presence of unseen small bodies. Is that Gail? Gail Chauvin, of the Max Planck Institute for Astronomy project, scientist for SPHERE and co-author of the study, explains, quote, "This data set is an astronomical treasure. It provides exceptional insights into the properties of debris disks and allows for deductions of smaller bodies like asteroids and comets in these systems, which are impossible to observe directly," unquote.
To understand why this is so important, it helps to look at our own cosmic neighborhood. Beyond the sun, the planets and dwarf planets such as Pluto, our solar system is crowded by smaller, minor bodies. Among these, astronomers are especially interested in objects that span from about a kilometer to several hundred kilometers in size. When such an object occasionally sheds gas and dust and develops a visible tail, we describe it as a comet. When it does not, we call it an asteroid.
These small bodies are time capsules. They preserve clues to the early stages of the solar system's history, when tiny dust grains gradually grew into larger and larger objects. In this growth process, bodies known as planetesimals represent an intermediate step between dust and full-fledged planets. Asteroids and comets are leftover planetesimals that never grew into larger planets. Isn't that sad? In the sense, small bodies are somewhat modified remnants of the raw material that once built worlds like our own Earth.
So cool. This is describing how this Earth, these planets come together, starting from small grains of whatever, sand, gold, arsenic, whatever, and they form together into comets and smash into other bodies to make a planet. You know what I mean?
Yeah.
Astronomers have now identified more than 6,000 exoplanets, that is, planets orbiting stars other than the sun.
Wow.
And we know that God's creations are, you can't count them, more than the sands of the sea.
Yep.
Revealing a remarkable variety of planetary systems and helping us place our own solar system in context. Actually taking pictures of these distant planets, however, is extremely difficult. Fewer than 100 exoplanets have been directly imaged so far, and even the largest ones usually appear as simple, featureless points of light.
The key, somewhat surprisingly, lies in material that is much smaller than the small bodies themselves. In young planetary systems, planetesimals Am I pronouncing that right? Testimal.
Yeah, like infinitesimal is just really, really tiny. A planetesimal is a tiny planet thing.
Okay. Planetesimals frequently collide. Sometimes they merge to form a larger body, and sometimes they fragment and fly apart. These impacts release huge amounts of fresh dust.
With the right instruments, this dust can be detected from very far away. The physics is straightforward. If you break an object into many smaller pieces, its total volume stays the same, but the combined surface area increases dramatically. If you start with an asteroid 1 kilometer wide and break it into dust grains only 1 micrometer across, or a millionth of a meter, the total surface area grows to a factor of 1 billion.
Because there is so much more surface to scatter starlight, the resulting dust cloud is much easier to see. By observing the light reflected by this dust, astronomers can infer the presence and properties of the small bodies that produced it. This is how debris disks around young stars become powerful tracers of hidden planetesimals.
As time passes, a debris disk does not remain static. Collisions become less common and the dust gradually disappears. Some grains are pushed out of the system by radiation pressure from the central star. Others are swept up by planets or planetesimals or spiral inward and eventually fall into the star itself.
Our solar system shows what remains after billions of years of evolution. Today, two major planetesimal belts survive. One is the asteroid belt between Mars and Jupiter. The other is a vast store of comets beyond the giant planets in a region called is that Kuiper or Kuiper belt? In addition, there is a population of dust within the plane of the solar system's orbits known as zodiacal dust. On very dark nights, you can see sunlight reflected by this dust shortly after sunset or before sunrise as a faint glow along the ecliptic called the zodiacal light. I don't know if I've ever known that before. So we can see that?
I never knew that either. Yeah.
So we should be able to see that.
Glow. Yeah, I guess we got to look. I guess, well, that glow, I've seen the glow before. I didn't know what it was, though. For an alien civilization observing from far away, this mature configuration would be hard to detect. In contrast, the new study shows that for relatively nearby systems, a dusty phase in a debris disk's first roughly 50 million years should be visible with the best modern telescopes and instruments. That does not mean the task is easy. Imaging a debris disk is comparable to photographing a faint puff of cigarette smoke hovering next to a powerful stadium floodlight while you are standing several kilometers away. Wow. In this demanding context, specialized instruments are essential, and SPHERE, that's the acronym, SPHERE, which began operations on one of ESO's very large telescopes in early 2014, is designed precisely for this challenge.
The central idea behind SPHERE can be understood from everyday experience. If the sun is shining directly into your eyes, you might raise your hand to block the glare so you can see the surrounding scene. SPHERE does something similar when it observes an exoplanet or a debris disk. It uses a chronograph, or debris disk. It uses a chronograph to block out most of the star's light, inserting a small disk into the optical path that removes the bright central glare before the image is recorded. This seemingly simple approach only works if the imaging is directly stable and precise.
To achieve the necessary performance, SPHERE uses an advanced form of adaptive optics. Light from different stars is distorted as it passes through Earth's turbulent atmosphere. SPHERE continually analyzes the distortions and corrects them in real time using a deformable mirror, which reshapes itself many times per second. Probably uses AI to do that. An additional optional component of SPHERE isolates light with specific properties, polarized light, that are characteristic of light scattered by dust grains rather than originating directly from a star. This filtering provides an extra boost in sensitivity for debris disk imaging.
The new study showcases a unique collection of debris disk images created with SPHERE by observing starlight reflected from tiny dust particles in these systems. Quote, to obtain this collection, we processed data from observations of 161 nearby young stars whose infrared emission strongly indicates the presence of a debris disk, says Natalia Engler, ETH Zurich. Is that a school maybe or a laboratory or something?
Yeah.
She's the lead author of the study. Going on with a quote, the resulting images show 51 debris disks with a variety of properties, some smaller, some larger. And that was the first slide you had up, right?
Yeah, I'm going to go back to it right there.
Yeah. Some seen from the side and some nearly face on, and a considerable diversity of disk structures. 4 of the disks had never been imaged before. That's cool.
Yeah. Here we go. There's the last slide there. Working with such a large and homogeneous sample is crucial for identifying patterns in how debris disks and their host stars behave. In this case, analyzing the dirty 51 disks and their stellar properties revealed clear trends. More massive young stars tend to host more massive debris disks. Disks where most of the dust and material reside farther from the star also tend to be more massive.
One of the most intriguing aspects of the sphere images lies in the internal structure of the disks. Many of them display ring-like or banded patterns with materials concentrated at particular distances from the central star. This arrangement closely resembles what we see in our solar system, where small bodies are grouped in the asteroid belt and in the, is that Kuiper again? Kuiper belt? Kuiper belt, which are comets.
These ring and belt features are widely thought to be shaped by planets, especially giant ones that clear paths in the surrounding material. Some of the giant planets responsible have already been detected. In other cases, details in the sphere images, such as sharp inner edges or distortions in the disk, strongly suggest the presence of planets that have not yet been observed directly. As a result, the Sphere Debris Disk Survey provides a rich set of targets for future facilities. The James Webb Telescope and ESO's Extremely Large Telescope, currently under construction by ESO, should be able, now it's different from very large, extremely large is different from very large. Currently under construction by ESO, should be able to capture direct images of at least some of the planets that are sculpting these intricate, dusty sculptures.
Well, not only this telescope, but the one that we had before, which I think is the Very Large Telescope, right? The other one that had the little beams of light coming out of it, or lasers or whatever they are. Those are pretty impressive looking structures. Not what you would typically think of as a telescope. So pretty cool.
Really cool. Yeah.
Yeah.
All right. We hope you enjoyed this segment. We'll catch you tomorrow, folks.
Take care, everyone. Have a good day.